the net work done on an object. So up until this point, we've done two things. We've looked at what happens when I have work done by an applied force, and then we looked at work done by a frictional force, and each of these were the only forces acting on an object. So I either had an applied force or I either had friction, but never both. Now when we talk about net work done, and the word net here, it means we're looking at the total. Now when we talk about net work being done, we will consider two forces or more acting on an object. Acting on an object, and as it acts on the objects, we've got to find the total work being done on the object by both forces. And when we do something like this, we have two different methods that we use. So if I'm looking at a situation, I must understand that to find the net work, I must add all the work that's been done. All right, let's have a look what we mean by that. Essentially, we need to calculate the total of amount of work that has been done. So to calculate the net work done on an object, right, we call that W net. We must calculate the work done by each force that's acting on that acts on the object. All right, so this whole thing happens while the object is being displaced. All right, so all we're doing is we are going to add up each contribution. So if the friction does something, the applied force does something, anything that does work on the object, we will have to consider that as work being done. Now that means I have two options. I have method 1, and in method 1 we look at W net, and the formula for W net is W1 plus W2 plus W3, etc. Or you can do method 2. I'm going to show you both methods, and that is when we look at F net is equal to F1 plus F2 plus F3. Then using the net force, we can go into the formula W is equal to F net delta X cos theta. So those are the two formulas. You will choose whichever formula you want to use. Essentially, you get the marks for both. So you decide where you're at with that. What you're going to need for this video is you're going to need to print out all of the documents which are in the folder. So the first document that you should have is your examples 10, 11, and 12. Those are the examples that we're going to be dealing with. Every time we do an example, all you've got to do is cut it out, stick it in your book, and we'll do all the calculations underneath that. It just saves you a little bit of time of having to write out each example. The second document that you need to print out and have with you is the notes, and we'll get to the notes. You will see when you need to print notes or stick certain notes. And then the last thing you should have is exercise 1, which is the exercise that you need to do after this video. Example 10. A force of 18 newtons is applied in the same direction as the displacement. So I've got 18 newtons, same direction as displacement. So I already know that I have a force applied. And when I have a force applied and it's in the same direction as the displacement, I know that the theta value is equal to 0 degrees. I then have a situation where it says I have a frictional force that acts in the opposite direction to the displacement. So that gives me friction, and I know that theta is always going to be 180 degrees because I've got my force applied here that's giving me positive work, and I have my friction that's giving me negative work. Alright, so I'm going to show you two, and I know that my displacement is 4 meters over here. So let's start with method 1. Right. For method 1, the first thing that you need to do is draw your free body diagram. So step 1, we draw a free body diagram. In this free body diagrams, we need to do a couple of things. The first thing that we need to do is we need to have all the forces. After we get all the forces, we must determine the angle of displacement and force. Is it 0? Is it 180? Is it 60? Whatever the case is. And we must look at direction of displacement. Right. So if I draw a free body diagram of this situation, I know my force applied is bigger than my frictional force, so I've got some sort of motion. It's got mass, so I've got here mg. Going to the right here, I've got 80, of force applied. Going up, I've got the normal force, and going to the side here, I've got the frictional force. So essentially, those are my 4 forces. Right, the second step that needs to be done is that you need to look at your formula. So the formula we use here is W net is equal to W1 plus W2 plus W3. Right, now the other thing that matters is what we put into this formula in terms of positive or negative matters. Which means when we start this question, we must make a decision as to what we consider a positive motion. So in this one, I'm going to say that anything that's moving to the right is considered positive. Which means that anything that moves to the left or in the opposite direction of motion would be considered negative when we sub it in. So this is in the direction of motion, and for negative values then in the opposite direction of motion. So either one, whichever one you want to use. Alright, so I know that W net is equal to W1 plus W2 plus W3. So here we're looking at all forces in the direction related to the displacement. And in this case, our displacement's in the x direction along the horizontal. Now, once we establish that, we need to decide what kind of work is being done. So I know that I've got a force applied and I've got a force of friction. So I'm only literally working with this horizontal directions. So I know I've got work done by force applied, and I've got work done by force of friction. So I need to, when I write down my formula, and I'm going to start now, please make sure you write down the correct formula. For example, you'll write W net is equal to the work done by the applied force. You can abbreviate it if you want, that's up to you, plus W of friction. Now all we do is we expand that information, or you expand those formulas. I know that W is equal to force applied times delta x cos theta plus force of friction delta x cos theta. And now I've just got to put in my information. So I know my force applied was 80. I know my displacement was 4 meters. I know it's cos, and I know that my force and my displacement are in the same direction. So that's cos 0 degrees. Plus, I've got a frictional force here of 20 times 4 times cos 180 degrees is equal to 80 times 4 is going to give me positive 320 joules plus negative 80 joules. And what my final answer looks like is 240 joules. And your answer can be left just as joules because it's a scalar quantity. And the last thing you've got to do is you're going to say, because this value is positive, I should say that positive work is done by the net forces on the object, and that means that the kinetic energy of the system will increase. Alright, so positive net work is done. I should put that on. Positive net work is done by the forces on the object, which means it increases the kinetic energy. And we can even say that the EK increases by 240 joules. So these little statements that we write, we continue writing them because essentially they assist us when it comes time to sort out our information after the question, the theory behind our answers. So just go through this one more time. Alright, so the first thing we look at is we draw a free body diagram. The second thing is we write down our formula. We identify all the forces. So identify all forces acting on an object. We then add those two forces together. What you will notice is if there's work done by friction, it will become a negative number because of the cos 180. So that's going to happen without you interfering with it. So you don't need to say forwards minus backwards or whatever the case is. You just have to work with the information that's been given to you. Once you solve that, remember, you've got to talk about the network. You've got to talk about the kinetic energy, and you can be specific about it. And that gives us method 1. Answer from method 1 was 240 joules. Look now at method 2. Method 2. The first thing we do with method 2 is we draw a diagram showing all forces which are in the same plane. Now what we mean by that is we're looking at anything that's in the x direction, right? Forwards, backwards, and so on. And what we do also further, we ignore all perpendicular forces. Now perpendicular forces are things like Fg or Mg or W or the normal force. The reason for that is that perpendicular forces do zero work on the object. Alright, so that's the first little thing. So let's have a look at the diagram we're going to draw. So I know that essentially, remember all these notes that I'm writing down here, you get them into your books. The first thing I've got here is I've got a little dot, and going across this way, I've got force applied, and that value is 80 newtons. And going in the opposite direction, I've got force of friction, and that is 20 newtons. So now I've got my forces in the x direction. Right, the second step you do is you calculate the resultant force. right, along the plane. And in this situation, the plane is in the x direction. So the first thing we're going to do is we're going to choose a positive direction. In this one, I'll keep with it and say that anything moving to the right is considered a positive motion. So make sure you choose a positive direction like we do in the previous step. The thing with method 2 now is instead of working out the work done by friction and then the work done by an applied force, what we actually just going to do is we're going to find F net. So you've got to find F net. You can either go F1 plus F2 plus F3, etc. Or you can go F net is equal to my forwards minus my backwards. Now when I'm looking at something like that, I can just say that my 80 Newton force is going to the right, so I'm considering that positive. So in this case, I can say 80 Newtons plus my second force. I'll just go here. I've got force applied plus force of friction. And I said this is positive 18 Newtons plus friction is always in the opposite direction of motion, negative 20. And what I'm left with now is 16 Newtons to the right. Or you can do forwards minus backwards. Your forward force is 18 Newtons minus your backward force, which is 20 Newtons. And you're left with 16 Newtons to the right. Now that is the 16 Newtons. It's your overall forces acting on an object. Right, your overall forces acting on the objects. So what we do now, step 3, we use that F net. So we calculate the work done on an object by taking the product of the F res, whatever you got, along the plane, right? And we look at this F res value, and because it's happening along the plane in one direction, we have to look at the angle. So if we choose this method, so make a note for yourself. If this method, method 2, is selected, right? If this method is selected, then you must identify the angle between the net force and the displacement. So in this case, our F res is still along the plane in a horizontal direction. It's now acting in the same direction as the displacement. So instead of me having a situation where I had that going and that going, I now have, so instead of having 18 Newtons there and 20 Newtons here, I technically have 60 Newtons going this way. My displacement is also to the right. So what I can say is that theta is equal to 0 degrees. If you choose this method, your theta always has to be 0 degrees where after you have worked out F net. It's very, very important. So what you will say now is that W net is equal to F net delta X cos theta. The F net we found out was 60. We know that the displacement is 4, and the theta cos is 0 degrees. You pop that into your calculator and you get positive 240 joules. So you'll notice that, and the answer for method 2 is also 240 joules. So therefore, the statement's a bit different. Positive work is done on the object as it increases the EK by 240 joules. That is very important that you mention positive work and that there is an increase in kinetic energy. So that's method 1 and method 2 for a basic question. And then we're going to get into other questions where it's not as simple. So let's have a look at a summary of what's going on. And at the bottom of your examples 10, 11, and 12, you would notice the summary. Just going to go through it quickly. This needs to be stuck in your books so that you have it with you. Work done is positive when the displacement of the object is in the direction of the applied force and that the angle between the force and the displacement is less than 90. When positive work is done, the kinetic energy of the object increases. When I have work done being negative, then the displacement of the object is in the direction opposite to the applied force and that the angle between the force and the displacement is greater than 90 but less than or equal to 180. Essentially, when negative work is done on an object, the kinetic energy of the object decreases. We then say that when work done is 0, when the displacement of the object is in the right angle or 90 degrees to the applied force. Another difference that we need to see or recognize is when we're looking at the difference between F and F net. When I'm looking at F and F net, F represents a single force. So that's when I'm looking at something like F applied. I'm looking at force of an engine. I'm looking at force of friction. All of those are considered just a force. When I'm looking at F net is the sum of forces. So if I'm looking for F net, then I know I've got to go F1 plus F2 plus F3, F4, and etc. Or I can say F net is equal to forwards minus backwards, essentially. When we're looking at work being done, we say W represents the work done by a single force. So that relates to work done by force applied, work done by force of an engine, work done by friction. So it's a single amount of work being done. And then when we look at net work, it's the sum of the work done by all the forces acting on an object. So our formula, I said, is W net is W1 plus W2 plus W3. And yes, the negative values will appear. And that's when you change the angle. So if I have angles at 0, then I'm going to get positive answers. If I have angles at 180, I'm going to get negative angles. It will sort itself out. You don't have to manipulate anything. Just put an addition sign in, pop it into your calculator. It should give you the correct answer. Let's have a look at the next example. So please notice for these examples, I'm going to be doing method 1 and method 2. Please feel free to pause videos if you feel like you want to work ahead or you can work ahead, so that you can develop some sort of independence before you start with exercise 1 a little later. Example 11. Consider a 4 kilogram block which slides 50 meters down a rough slope inclined at 30 degrees to the horizontal, and the block experiences a frictional force of 15 newtons. So what I want to do essentially now is get down all my information. I've got here my mass, which is equal to 4 kilograms. I've got a displacement equal to 50 meters. Please notice that this zone over here is considered the height, how high the slope is. But going down the slope, that's the distance. I've got an incline, theta value equal to 30 degrees. And I've got force of friction, which is equal to 15 newtons. And a couple of things I have to consider is that this object slides, which means there is no applied force. It just goes down naturally, so that sliding motion is natural, and because it's a rough slope, I am going to get some friction that's going to oppose that. All right, let's start with method 1. All right, this is very important for method 1. If this is your preferred method, you need to be able to do a proper free body diagram. So when we do method 1, we use a net force free body diagram. So what I'm going to look at is I've got my object here. I know that it's sliding down and I've got some sort of mg over there. Or let's make it fg so you know it's gravity. Going up my slope here, perpendicular to my slope, I've got my normal force. And then I've got the object sliding down, but something's resisting that object, and that is the force of friction. Right, this part is important. Please make sure you use a ruler or whatever the case is. What I need to do is I'm just going to represent my incline here. So I've got my incline here. And of my incline, I know that this is 30 degrees. And I also know that there is 90. Now what I'm looking at is if an object slides down, it's sliding down, it means that the thing that's bringing it down is going to be gravity. So my theta value is over here. And this theta value, let's do it in another color so that it doesn't confuse our diagram. This theta value is always between the FG or mg or w, whatever you're going to call it, and the displacement. So this works for if something is going to slide down. That is where we're going to find the angle. So if this angle here is 90 degrees and this angle is 30 degrees, then my theta value here is equal to 60 degrees. Now in this situation, we have a weight that is acting. So you need to understand this. The weight is acting at 60 degrees to the displacement. So our force that's going to bring this whole thing down is Fg. So Fg is the cause of the box sliding down. All right, it's gravity, which is down. It's a natural force. It's the natural force of gravity. So when I'm looking at my little setup now, I've got to make decisions about my theta values. I know that Fg is down the slope at 60 degrees to the displacement. And I know that I have a force of friction, and that's acting upwards. Oh, let's go up the slope at 180 degrees to the displacement. So how do I see that 180 degrees that I'm talking about? Let's use a color. Have a look here. If I draw an angle here, I've got the thing that brings my object down here is Fg. And 180 degrees to that Fg is my force of friction. So the angle there is 180. So that's how I get 180. It is in the opposite direction. So my friction is in the opposite direction to Fg going down the slope. That's my motion of my object here. All right, so I have two forces acting on this object. If it's sliding, I've got gravity that brings it down, and I've also got force of friction, which is forcing it to stay on the incline. So when I'm looking at my formula for method number, or method 2, I can say that W net is equal to W1 plus W2. So what I've got here is the work done by Fg plus the work done by friction. So my formula now reads mg, which is my Fg, cos theta, plus force of friction, delta x cos theta. So remember at the beginning I've written down my information. So let's have a look at how this looks. I've got 4 times 9.8. My distance was 50 meters cos, and my gravity was at 60 degrees to the displacement. Times force of friction was 15 multiplied by 50 cos 180 degrees. So what I'm left with here is positive 980 plus minus 750 joules. So what I'm actually seeing here is that I can see now that the work done by the weight of the object is positive. This is just a sidebar. On the other side, I can see that the work done by friction has to be always negative. Right? Friction cannot do positive work on an object. It's just not possible. So I add that together and I'm left with 200, positive 230 joules. That's my answer. So what I can say here is that positive net work is done on the block and the kinetic energy increases by 230 joules. Now, if this calculation is too overwhelming, you could always go work done by the force of gravity is equal to Fg delta x cos theta, which is going to give you mg delta x cos theta. And I know that that's going to be 4 times 9.8 times 50 cos 60, and that gives me 980 joules. And on next to it, I can do force of friction, or work done by friction, and I can have force of friction delta x cos theta, 15 times 50 cos 180, and that's going to give me negative 750 joules. I can then come through and say W net is equal to work done by Fg plus work done by force of friction, and I'm going to end up with 980 plus negative 750, and that's going to give me 230 joules. So either way, that statement still applies, that positive net work is done on the block. The kinetic energy increases by 230 joules. You can split it up if the math altogether gets a little bit confusing. So again, how we do this is we sort out our net forces, we sort out our angles. Once we've sorted out, we need to find out what's bringing it down the slope, what's forcing it to go up the slope. Make decisions about theta, that's very important. Make these decisions here. Substitute into your formula, write down your statements. There's 2 ways of doing method 1. For the same example, I'm going to do method 2, and let's have a look at how that plays out. Like I said, if it's 230 joules, then I've got positive net work done on the block, and the kinetic energy increases. Right, for method 2, the first thing we need to do is we need to draw only the forces that are acting along the plane. To show all forces acting on the slope. So this time we don't have an x direction, we have some sort of slope. The other thing is we know we need to ignore all perpendicular forces because they don't influence anything. And I know they do zero work. So we don't have to show F perpendicular and F parallel. So what we do is, for method 2, we're going to do a component free body diagram. So I've got my force, my little dot over there. I know I've got the normal force there. And I know that I've got going this way F perpendicular. Now what I need to actually be focused on is what is happening on the slope. So if I look on the slope, I know that going upwards, I definitely have a force of friction. But going down the slope, I've got my F parallel, which is mg sine theta. So our focus is on mg sine theta. So understand something, that the force of friction here is parallel to the surface, right? But it is moving up and therefore is in the opposite direction to the parallel component, which is F parallel. Again, I'm going to just reiterate that Fn and Fy, or I can even say F perpendicular, will do zero work on the block. So we're not going to take that into consideration. What we do understand is that this F parallel here is the force that allows, so this here is the force that allows the block to come down the slope, right? And we know that this F parallel acts at 30 degrees to the horizontal. So that's another thing that's important. So remember, for this one, we don't work out just work done, we work out F net first. So if I had to look at my F net formula, I'll say F net is equal to my forwards minus my backwards. I'm showing you different methods so you can see how you'll sort that out. Now, what brings the block down the slope is always considered forwards. So your F parallel is always going to be a forward force. And I know that force of friction is always in the opposite direction. So that has to be my minus. So my forward is going to be F parallel minus my force of friction. Now my F parallel here is always mg sine theta minus my force of friction, which they give you at 15. So I'm just going to go 4 times 9.8 sine 30 degrees minus 15. Now this is important. This sine 30 degrees here is because your F parallel is at an angle of 30 degrees. Right, so what we're doing when we mean by the same plane, the plane we're working on is not a horizontal surface, it's a slope. And the only forces that are acting along that plane is your mg sine theta and your force of friction. So now you're left with 19.6 minus 15, and that means your F net is equal to 4.6 newtons down the slope, or in the direction of motion. Right, up to you there, how you're going to write down your forward direction. And the third thing that needs to be done is we need to find the net work done. Done using the information that we have. So to calculate the net work done on the object, we're going to take the product of the resultant force, which is my F net there, acting on the object along that plane. And essentially, remember what we said, if they're on the same plane, it means they can either be at 180 or 0. Considering the fact that our F net here was positive, and it means it's going down the slope, the force is in the same direction as the displacement, which is the force is down the slope and the displacement is also down the slope. So what I'm actually looking at is, if I had this, I've got my little block here. I had my friction going this way at 15 newtons. I had my mg sine theta here at 19.6 newtons. I did a calculation, and essentially now I've got going down this way 4.6 newtons. That's my setup. So if I had to look at that, I would say W net is equal to F net delta x cos theta, and the F net is 4.6 times 50 cos 0 degrees. So remember what I said in the previous example. If it's on the same plane, then theta is equal to 0 degrees always. So that gives me a total of 230 joules. And you've got to write down those things. You've got to talk about positive work being done. And you've got to say that the kinetic energy increases by 230 joules. So that's method 1 and that's method 2. And that's how we sort that information out. So far we've looked at object just slides down affected by friction. We've looked at objects on a horizontal surface where there's a forward force and friction. Now we're going to look at another example that's both a forward force and there's friction and there's an incline. Alright, before we get into our two methods, there is the second worksheet, the notes worksheet. And that just gives you your summaries, which I think you should just stick into your book so that you have your summaries with you. So this little summary deals with net work done. And let's have a look at the two methods. For method 1, we draw a free body diagram and we show all forces acting on an object. We need to determine the angle between each force and the direction of the displacement. And then we use W is equal to F cos theta to determine the work done by each force. So this F here can be Fg, force of friction, force of the engine, driving force. Right? That F will change each time. And then what we do is we look at the sum of all the work done using the formula W net is equal to W1 plus W2 plus W3, etc. The second thing we look at is method 2. We draw a free body diagram along the plane of the motion. We ignore perpendicular forces because they do 0 work on the object. We then calculate the net force, or you can call it the F res, which is the sum of all forces acting on that object. Sum of all forces acting parallel to the plane. And you got your F net, which is F1, F2, F3, or forwards minus backwards, whichever formula suits you. You then calculate the work done on an object. Sorry, that should be an object. Substituting the F net into the formula, W net is equal to F net delta x cos theta. That F net value should come from after you worked out the actual F net. So the methods are your choice. This is just a summary of your methods that's in your book so that when you're studying, you have some point of reference. Let's have a look at the last example here. Example 12. It says, consider a car that has a mass of 800 kilograms, which drives 80 meters up a rough slope inclined at 30 degrees to the horizontal. The car engine applies a forward force of 8,000 newtons and the car experiences a frictional force of 2,500 newtons. Calculate the net work done on the car. So the first thing that we want to do here is we want to identify all the forces that are taking place on this system. Right, the first thing I have is mass, which is 800 kilograms. And it says it drives up a 80-meter slope. So I know my displacement is equal to 80 meters. And that the slope is inclined, so my incline theta value is 30 degrees. And then let's look at the forces. The first force I have is the car engine applies a forward force. So I have a forward force, and that forward force is 8,000 newtons. I've then, of the engine, I then have a frictional force of 2,500 newtons, and that's force of friction of the slope. And they want the total net work done. So let's have a look at how we draw free body diagrams here. So I've got my object over here. I'm doing method 1. So method 1. I've got my FG over here going up perpendicular to the incline is my normal force. My car now, this is important. It says the car drives up the hill. So what we consider a forward motion is that motion up the hill. So going up the hill, I've got my forward motion, my force of my engine. But coming down the slope, I've got, together with my force of gravity, I've got the force of friction. So remember in the previous example, I said that you must extend your incline so that you can sort out angles. So here's a couple of things. That's at 30 degrees. And I know that this here is at 60 degrees. So here's my situation. I've got an engine force here that is going up the slope. And that's my direction of motion. And I've got my force of friction, which is in the opposite direction of motion. And the fact that I've got an incline means I've got gravity, which is going to be down the slope. So I've got the friction also going down the slope. Right, so when I'm looking at this, I need to look at all the angles at which these forces are operating. For instance, I know that, I'm just going to redraw this whole thing, so just bear with me. Alright, so if I'm looking at this setup that we've got here, the first thing, in this example, the displacement, your delta x, is up the slope. That's important. So anything that goes up the slope would be in the direction of the displacement. Now, we've got three things happening here. We've got your force of your engine, which is going up the slope. And we've got friction, which is going down the slope. And we've got gravity that's also going to bring the object naturally down the slope. So we've got to look at what is happening with each of these, and we've got to find their angles. So let's have a look here. The first angle I'm looking at is the object coming down the slope due to gravity. So I'm going to look at the angle between the displacement. So I'm just going to highlight this in pink. Your displacement is that area over there. Right, so your displacement is up the slope like this. All right, let's have a look at the first little bit. When your object was sliding down, then the force of gravity was bringing it down the slope. So this angle here was 60 degrees. But now your FG must act to the direction of the displacement. Your displacement now is going up the slope. So the angle we look at is this angle. 180 minus 60 is going to give me 120. So for gravity, I'm just going to write it down here. I'm going to say that the weight acts at 120 degrees to the direction of the displacement. So when the displacement was down the slope, right, then that 60 degrees here made sense. But now the displacement is up the slope. So your weight in this instance, or your weight here, so the FG or your weight, right, does negative work. The reason why it's doing negative work is because it's no longer with the engine. It's going in the opposite direction of motion. It's bringing it down when the goal here is to get that car to go up the slope. So your work done, the theta angle we use here, your work done by force of gravity is, your theta value is equal to 120 degrees. So that's the first degree that you've got there. If I look at friction, friction now is going down the slope. And when I compare it to whatever's going up the slope, I can have a look at that angle and see the angle for force of friction in green here is 180 degrees. So for friction, the force of friction acts at 180 degrees to the displacement up the slope. Right? So the displacement is up the slope and the friction is going, force of friction goes down, which means now the friction does negative work on the object because it's going in the opposite direction. So we can say that for work done by force of friction, your theta value is going to be 180 degrees. Now, if I look at the force of the engine, and that is going upwards here, can you see that the engine, and if I look at the pink line, the engine and the displacement are in the same direction. So the force of the engine, force of your engine is going, up the slope, but your displacement is also going up the slope. So therefore my force of my engine is like a force applied by the engine, and that acts at 0 degrees to the displacement. They're in the same direction. Therefore it does positive work on the object. So for the work done by the engine, for theta, I've got it equal to 0 degrees. So if for each of these, what we had to kind of do is, we had to find for our formulas for method 1, what were all the values of theta. And it's a little bit different to the examples because it is a level 3, level 4, even a level 5 kind of question that we have to sort out all of these angles. So let's get into the actual calculation here and let's see what we've got. Right. So I know that W net is equal to W1 plus W2 plus W3. So this time I have three forces acting on my object. The first force I have acting on my object is the work done by my gravity force plus the work done by my friction force, and then plus the work done by the engine. Alright, so I've got mg delta x cos theta plus friction delta x cos theta plus force applied of the engine delta x cos theta. And all I'm going to do is enter all my information into it. My mass is 800 times 9.8. The distance of this whole thing was 80 times cos, and for my weight it was 120 degrees. Plus my frictional force. I know my frictional force. I wrote down that information. Was 2,500 newtons. Just go all the way down here. 2,500 times 80 times cos 180 degrees plus my force of my engine, which they tell me is 8,000 at the beginning, times 80 times cos 0 degrees. So if I pop all of that into my calculator, for gravity I should get a negative value. For friction I should get a negative value, but for my force of my engine I should get a positive value. And if I put all of that together, I'm going to get 126,400 joules. Alright, so that's method 1, and I can say therefore positive work is done on the car, and that the kinetic energy of the car increases by 126,400 joules. Right? I could have done this a separate way. I could have done each one of these separately and then added it together, looking at the W net, W1 plus W plus W3 method, which looks like, right, where you could have done the work done by gravity and got negative 313,600 joules. Work done by friction, you would have got negative 200,000 joules. And then you could have done the third thing, which was work done by the engine. You got 640,000 joules. And then the final thing that you could have done there is W net is equal to three forces, 1, 2, 3, and you still get the same answer. It depends how you would like to do a method 1. The biggest thing about method 1 is sorting out those angles, where I think method 2 may be a better option, as it provides us with less analyzing to do, and rather more working with things that we do understand, like for example when we do Newton's laws and we do know how to work it forwards, minus, backwards. Alright, for method 2, the first thing you need is your free body diagram, and in this one we're doing components. So let's have a look at what's going on. I'm just putting this in here. That's my force of my normal, and down over here I've got mg cos theta. Right, now I've got to put in my actual forces. I know that going up this slope is my force of my engine, and in this instance here I'm going to take the engine force, the upward force, as something positive. Going down your slope, the natural thing that's going to bring it down is gravity, and the sign we show for that is mg sine theta. But because your surface already has a very rough surface, I have my force of friction as well coming through over there. So now on this plane, my let's have a look here. On this plane, my force of the engine, my force of friction, and my mg sine theta, which is my force parallel, are all in the same plane. They all are along the slope. So what I can do is, once I've sorted that out and I understand that these two forces here are going downwards and my engine force is going upwards, I can look at F net. So all I'm going to say is F net is equal to whatever is considered forward minus all of the things I'm considering backwards. So anything that goes up is positive and anything that goes down is negative. So in this instance, I've got my force of my engine, which is forward, minus the force of friction, minus my F parallel. So I've got here 8,000, which they give you in your question, minus 2,500, minus, remember this here is, I'll just put it here, mg sine theta, which is 800 times 9.8 sine 30 degrees. Don't forget that this 30 degrees has nothing to do along the slope. The 30 degrees is of the incline. And that will give me a total of 3920. So essentially I'm looking at that F net value, and my F net for this thing on one plane is 1580 newtons up the slope. So it looks like up the slope is 1. And because they're all in one plane and we looked at the net force, I know that because it's up the slope, the theta value we have to use is 0 degrees. Now, if this was a negative, let's make a note here. If negative, then theta must be equal to 180 degrees. But now this time it was positive, so we don't have to worry about that. So I'll say W net is equal to F net delta X cos theta, which is equal to 1580 multiplied by 80 cos 0 degrees, and that gives me 126,400 joules. And essentially there I end up saying, therefore, positive work is done on the car, and that therefore the kinetic energy increases by 128,400 joules. Mechanical energy has been added. So you can choose method 1 or method 2, but that's the situation. Along the next little thing that you would have seen on your little worksheet is this little summary that says the work done in an object by a constant force is F delta X cos theta, where F is the magnitude of the force, X is the magnitude of the displacement, and theta is the angle between the force and the displacement, giving us this formula we've been using. Like we say, if negative work is done, then energy is removed from the object. When we're looking at net work, like I said, W net is equal to W1 plus W2 plus W3 plus W4, and we use all of the forces, and that gives me method 1. In another instance, I could use method 2, and that gives me W net is equal to F net times delta X cos theta, and we use components when we calculate F net, and that gives me method 2. So that's the second little bit of a summary that you need to stick into your books. Once you've stuck that into your books, also in this drive folder for lesson 4, it says exercise 1. Exercise 1 is a worksheet that needs to be completed. Work independently. You can print the worksheet out, stick it in your book, get through all the examples, and then when you watch your next video or whatever, you can see the memo for this this worksheet or whatever the case is. And then once you're done with the worksheet, proceed to the folder that says lesson 5, and you can get going with the next lesson.